Alright, and back to me. 5, 4, 3, 2, 1. Lauren, give me an example, or you and William, give me an example of a cation, anion, or somehow explain the difference between them.
Okay, so a cation has more electrons and protons.
Cats are.
More
Okay, so in this version, there are more protons than electrons overall. What about anions? Okay, so we're just doing little inequality symbols there. Irie and Brendan, give me an example, or how would that situation even happen? Like, how would that be formed?
So, like, you had hydrogen with a negative charge or something.
So, but how did it get that negative charge?
It lost an electron.
It's one or the other. It can't be both.
It gained an electron.
Okay, so if something is a negative charge, it gained an electron. All right. Up here, Omar and Jacob, give me an example of how I could form a cation then.
It lost an electron.
Beautiful. Okay, so it's positive because it lost an electron. I was really hoping nobody would ever say the word lost or gain of a proton, so that's what I was looking for there. So the example would be, let's see, I heard hydrogen, so you could have hydrogen 1 plus, meaning it gained, it lost a proton, electron, and then hydrogen 1 minus could be a gain. So something like that. So notice we're saying ions, and the word, that word is in the names. And ion, cation, those are ions. All right, so kind of following up there, what subatomic particle always stays the same? Bradley and Syrian.
Proton.
Protons. Okay, unless you're doing nuclear decay, which we'll get to at the end of the unit, but this is by far a majority. What subatomic particle changes to create an ion? John and Frank? To create an ion. So we just use this word. Where do we just use this word? Mm-hmm. And what were we talking about was changing up here?
Electrons.
Thank you. So what subatomic particle changes, is lost or gained in order to create an ion? Electrons, right. Can't be the proton, because then we just said that we changed the identity. That's just a wash. We didn't say anything about neutrons yet, because neutrons in the subatomic particle realm, it's a neutral species, so it doesn't create any kind of charge, positive or negative differences. So, but if you do change that subatomic particle, it can change something else. So, leading into that, what subatomic particle creates a different isotope? Sandra. Number of neutrons, right? And so when I change the number of neutrons, what is it actually doing with the overall atom? What is it actually changing? Is it changing the atomic number? Is it changing the charge? Thank you. It's changing the atomic mass, or mass number. And so when it changes the mass number, that means that it's just a heavier isotope or a lighter isotope, but it's still the same element. Okay, those vocabulary terms are really not that difficult, but if you start using them in context, I think it helps you remember the relationships between them. So that's kind of step one of review. Let's hit up another part of review. Question, I'm sorry. Okay, let's do one more review. You guys do these two, actually do those first three, okay? So the person next to you, chat about it. You have your table in front of you. Write this down so I know you're engaged with it.
I think that's really first. Oh no, the proton is 13. And then the 29 is the neutron. You get electron. So that's not a, so 13 would be the proton, the electrons would be 16 plus 3. And then the neutron is 29 minus 13. 16. Yeah, it's just mass.
Really? Really?
6 protons. So then you get 29 minus 2 electrons.
Take about 30 more seconds.
The electrons is 47. Yes, and then 109 minus 46.
All right, I'm going to just go in groups here, okay? So this whole little area will be the first row, second area, second row, third area, third row, okay? So protons, let's go, guys.
13.
How do you know 13 off the bat? Bottom number, atomic number 13, proton number 13. What else also could be 13, but we have to modify it? Electrons could be 13 if it were neutral, but it's not, so 10, because it's 3 plus, meaning it lost 3 electrons. 10. And then neutrons. How did you do that?
29 minus 13.
Look, it lines up so perfectly. 29 minus 13 is 16 neutrons. Great. Okay, give me a thumbs up if you guys are good on that one. Okay, you have like your chart almost exactly like this on your test, so I just want to make sure you're clear. Like stuff we do in classes, it mirrors kind of what you do, we'll do on your test. Next group, ready? Go for it. Protons.
6.
How do you know that? Atomic number 6. Okay, what else could have been 6? The electrons, but it's not. What is it? 10, because you add 4 electrons because it's negative charge here, okay? Neutrons? 8. And how do you do that math? 14 minus 6 is 8. Beautiful. And so the first one is an example of a, what would you describe this guy as? Say again? One more time. Cation. Okay, this is a cation. It's positively charged. This is an anion. Okay, and then this is just a plain old isotope. Okay, so because there was really not a lot of information here, group, what do you have to do? Look at the periodic table. What do you know about protons?
That's 47 protons.
Because it's atomic number 47. And then what else?
6.
Oh, sorry. That means also your electron count is the same because of the whole neutrality here. And then lastly?
62 neutrons.
So you did 109 as the total mass minus 47 to give you 62 neutrons. Notice the neutrons and protons don't have to be equal. They might be equal, but they don't have to be. So I'm trying to force that relationship. Okay, I'm feeling pretty good about that. Let's jump to stuff from Friday. Okay, so the video that you guys watched, it's one of the more math-heavy sides of the relationships in this unit. It's just the electromagnetic spectrum, speed of light. There's 2 formulas you should have learned, and then on the POGL, which I should probably give back to you, but I'm going to give that back to you at the end of class. It talked about like Bohr's model and about how light is generated and so forth. So, do you guys have your notes? Yes? You're guys going to tell me a couple of things that you learned as a quick review. So, one second. So, as we go, I'm going to stop and we're going to do some problems within. The problems that I'm doing are from problem set 5. So, I'm knocking out some of those with you, okay? So, make sure you organize yourself enough to know that we are doing some problem set 5 stuff. Question, Cassandra? Okay, work with Ishmael then for a second because I will have to hunt for that in just 1 second, okay? All right, so, oops. All right. space. All right, I want to hear facts or equations or constants, anything you want to talk about, okay? Go for it. Okay, what about it?
You cannot determine where the wave is or its frequency.
Or, so it's location or it's speed, I guess, frequency.
Yeah.
No, you're right, frequency. Frequency does relate to how fast things are moving or how frequently it comes by a location, so it does relate to speed. All right, so uncertainty principle relates to location and speed, aka frequency, which is that little V for the tail. I don't think I told my jokes on video, so you ready? Okay, so Heisenberg and Heisenberg and one of his fellow chemists driving down the road. Behind him, it goes, whoop, whoop. Police man pulls him over. He goes, sir, do you know how fast you were going? He's like, no. He said, you were going 110 miles an hour. He's like, well, great. Now we don't know where we are. Because you can't know the location and the speed in a lifetime. Because once you know more about the location, you know less about the speed. Once you know more about the speed, you know less about the location. So they got lost. Because you guys. Okay, well, it's the joke of the day. Okay. Next fact. Let me get two more over here. Yeah.
Speed of light is c equals 3.7
Meters per second. Guess what? We're going to be using that a lot. Make sure you memorize that. Let me come back to this group in a second. Next group, tell me some factoids. What equation will we use with the speed of light? Okay, so wavelength is that upside down broom, right? Upside down Y, lambda. Frequency is a V with a tail. So if the speed of light is in meters per second, what will the wavelength unit be? Think of length. Meters, okay? What will this frequency units be? Not just seconds. Per second, right? 1 over second could be a way you could write it. Seconds to the -1 is another way to write it, or hertz. It's just this guy named Dr. Hertz or whatever named it after himself, but it's not really all that informative, so I generally don't use hertz a whole lot. I'll use seconds mostly. But you should see a definite relationship, because any equation with things that were set equal to each other, their units should match up. So meters and meters, and then per second and per second, so that kind of shows you there's a relationship there. Though many times I will not give you straight up meters for the wavelength. I could also give you what other unit. Say again? Nanometers. You would have seen that a couple times, both video and on your worksheet. So I could give you nanometers, and now that means you have to think about how King Henry died, get to your nano, and then convert between meters and nanometers. Okay, we'll do that in just a second. All right, so there's another equation that comes along with this. Anybody else? Let's go. As much feedback as I can get because we have a lab shortly. Okay, so Planck comes into play.
Energy equals constant speed.
Okay, stop there for a second. So you see the commonality between these two equations, right? What's the common variable? V, which is frequency. So frequency is the common variable. You should know how it relates to every other variable. So if frequency, meaning something is moving really, really, really fast, so high frequency moves really, really fast, how long is its wavelength? Very short. Okay, so if things are moving really, 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 really fast, they can penetrate your skin, they can mutate your DNA, and then you turn to the Hulk. That's gamma rays for you. But then you guys listen to the radio, right? Okay, everybody listens to the radio. Radio waves are really long and slow. Okay, so they're huge. They're like 1,000 meters long. They're just a form of energy that hits our little cilia in our ears and and then they move and they transfer to our brain and say, hey, we're hearing this. But they're still energy. So the longer the wavelength, the slower the wave. The shorter the wavelength, the faster the wave. So you tell me, does really long radio waves sound like it's got a lot of energy? No. So that's why you see that this being inversely related, because this is a constant, will actually give us some more information about how energy and frequency are related as well. So you just told me fast waves have a lot or a little bit of energy. fast waves move really fast, they have a high speed. That means that as frequency goes up, energy also goes up. That's because this is a constant. The constant cannot change. So these two things are directly related to each other. Whereas wavelength and frequency are not directly, what's the opposite word? Indirectly or inverse, right? Inversely related or indirectly related as compared to frequency and energy. Now, what's this guy's constant? 6 units. Joules times seconds. Joules times seconds. Okay, so that's the constant units, joules times seconds. And that's what this is right here. Joules times seconds. Let me make this a little bit neater. This is joules times seconds. What does energy always come in? What unit? Just what?
Joules.
Just joules. Okay, so that's just joules. Then joules equals joules times seconds times what for frequency? What's frequency's units? One more time. Inverse second, or 1/second as I like to show it. And what does that show you can happen with this, all this over here? Seconds can cancel, which gives us just joules. So that's how you should see the perspective of the unit. How is it helping you solve problems? And noting that it's really important to write it down, because what if I give you nanometers and you just pop it in the speed of light equation? You're going to be like a billion off. Okay, that's a large % error there. You don't want that kind of error. Okay, so we kind of talked about, there's stuff called energy in the electromagnetic spectrum. Give me some examples of different types of energy. Shout them out. Let's go. I can pull out the cards, but I was really hoping that you guys could give me some feedback. Gamma rays, okay. What else? X-rays, what else? UV, so ultraviolet. We got some of that on Saturday. It's a nice day out, or yesterday, yeah. Okay, what else? Microwaves. Okay, what else?
Radars.
Radio waves.
Radio waves, I'll kind of lump that with radar. Yeah, I think. There's one more.
In your textbook, it was in like 2 different groups.
Radar.
Waves and radar.
Radar. We don't generally, it's like sonar. It's related to radio, but it's not exactly the same. I'll write that here as well. But there's one more big one we're missing. Say again? Well, so a lot of these could be classified on the short side or the long side. That's too broad. Visible! That's what we're talking about. Okay, visible. And you'll see that you'll start to think, how does visible kind of come into play? Well, it's the only one that we can appreciably see. We feel the other stuff, right? It burns our skin. We can see the other one because it puts us on this like X-ray graph. We could actually allow light to come in our eyes and give us some visuals to that. So we know these other ones exist. We just can't see them. So when we do our lab today, which we will actually be seeing light, right? Well, we see it all the time, but we're going to see it from a very specific instance. Where the heck is this light coming from? What did you learn in the video that creates visible light? Cassie, for Cassandra. Okay, so electrons moving. I'm going to use some general words first, and then I'll jump into the exact. So electrons moving from excited, actually, let's go higher energy to lower energy. That's all really that's causing this different versions of light, which we call different colors of light. But the different colors of light are only different colors because they come in different what? Anybody? Different. It's probably a little bit of some of. I heard sizes. What's another word to describe size of something? Say again. Wavelength, length, okay? Which, of course, if it comes in different wavelength, it comes with different frequencies and different energies, because all those variables 100% are related to each other, either directly or indirectly, like we just said above. But if you can say, okay, it's moving from a high level of energy to a low level of energy, where's the extra energy going? Say again? So it's being released as light, right? So as you drop from a high, this is called a high energy level, EL energy level, okay? If you have a high energy level, which while I'm there, I think I showed a quick picture of this on the, or I referenced this in the video. Go ahead and pull out this reference sheet that I just gave to you guys. There's a couple of them floating around. Look on the very back side, it has the Bohr diagram. So, who's Bohr in my scientist groups? Who's Bohr? Here's a like, what scientist group? What? Okay, so I have one Bohr person. There's probably more of you, but we'll get there. All right. So Bohr's diagram is here. It gives us these very specific orbits and concentric circles around the atom. If I said, tell me the energy that's related to the drop from energy level 5 to energy level 2, track the changes. Look for energy level 5. It's called n equals 5. And then, actually, let's drop to energy level 1 because that's what I'm looking at now. So drop from energy level 5, N5, to N1. You see the dashed line as it kind of shoots off that difference? What number is associated with that? See? Oh, I'm on the wrong one. Energy level 5. Sorry, these are little. Energy level 5. Oh, there is no 1, is there? I'm looking at 4 at 1. Let me go back to my original example. I said n equals 5 to n equals 2. You see n equals 5 to n equals 2? That's 434. Am I right? Okay, 434 what? What does that number mean? Yeah, look at the labels. You guys can read a graph. You don't need me to help you read that graph. So if you're going from low energy or high energy level of n equals 5, dropping to lower energy level of n equals 2, there's this wavelength of light given off that has 434 nanometers in length. Because at the very top of the chart, it says hydrogen atom, it says measured in nanometers. Okay, that's the wavelength, right? From there, we can find every other piece of information we want to find. Specifically, 434 is what color of light? I don't know. How much energy does it have? I don't know. What's the frequency of it? I don't know. Let's do that now. Write down this information. We're solving this one together. And label your identities. If you need a calculator, I'll pass you one in a second. So that's the wavelength. Do you guys want to find the energy first, or do you guys want to find the frequency first? Let's find frequency, because if we're going to energy, we've got to go through 2 extra steps. That'll be our final conclusion. All right, so let's solve for frequency. What equation pulls those 2 variables together? C equals wavelength times frequency. Okay, wavelength times frequency is equal to C. What is C? So 3.00 times 10 to the 8th, what? Meters per second. Okay, so that's the information we know. This is in meters. What's that in? Oh, it doesn't match, right? Apples and oranges, we can't compare that just yet. Let's get them to comparable units. So which would you guys prefer to convert? Nanometers to meters or meters to nanometers? Yeah, let's do nanometers to meters. And generally, we kind of try to keep that constant what it is, so we'll convert our stuff to the units within that constant. So let's do that now. 434 nanometers. Dimensional analysis is the process of taking units and canceling them out with other units by using equivalencies. What is the equivalency I want to write here? I want to convert to what? 2 meters. So where does meter go? Top. Okay. How far away is nano from meter? If you need to write out your King Henry died by drinking chocolate milk. ... Micro ... Nano ... Pico ... Mega. Okay. So given that, where's base at here? Where's it at? B. I'm sorry. Where's meter at here? Meter is at base. I was really hoping you would say M, because that's milli, not meter. So we're how many spaces away? If base is a 1, because it's the bigger unit, how many spaces away? 9 zeros. Ain't nobody got time to write 9 zeros. 10 to the 9th nanometers. Please don't waste your time. And I only say that because I'm giving your test back today, and some of you guys wrote the wrong number of zeros for a question that you could have gotten full credit on. I try to give you most of your points, but whenever you're doing this, you always want to put the 1 at the unit, that's the bigger unit, and then add zeros from the 1. Don't count the 1 as a 0 space, because there is a difference between that, because you're actually saying now that's another 10 times greater. So every place there's a 0, that's 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 to the 9th is how you can write that very quickly. Okay, so nanometers and nanometers can go away, and that is 4.34 times 10 to the negative 7th meters. That is the wavelength. Now it's in meters. So taking this information, C is equal to wavelength times frequency. I want to solve for which of these variables? So I want to solve for frequency. How can I rearrange this equation to solve for frequency? Divide by wavelength on both sides, right? So you guys are good. So wavelength is going to divide out that side. That's good. Frequency is by itself. I need to do C divided by wavelength. So I need to do what over what? Times 10 to the 8th meters per second divided by 4.34 times 10 to the negative 7th meters. First off, what unit cancels and what stays? Meters on top and meters on bottom cancel. What unit stays? I heard it. Per second. That slash second means per second at the end. If you put this in your calculator wrong, what's going to happen is your calculator is going to think you're multiplying by 10 to the 8th and you're dividing, and you're like, oh, but then multiply by 10 to the negative 7th. No. You want to divide by using parentheses so your calculator understands what you're doing. So I'll pass on. You guys need to bring this so that you understand how to use your calculator, unless you always want to do something, because it's sometimes hard to calculate and faster than others. You end up doing something wrong with the other calculator. Alright, I'm going to finish up after this example, and then I've got a little bit more to take up light, and then we're moving on to lab. Calculate it. Anybody? Anybody? So I hear 6.91 times 10 to the 14th. Does anybody else get that? Okay, so frequency is equal to 6.91 times 10 to the 14th what? Per second, right. So that means that thing is moving like, what's more than a billion? Trillion? Is that a trillion?
Yeah.
More than a trillion times per second. The frequency is causing the wavelength to move that fast. That baby is moving fast, right? Alright, so that thing is moving fast, which also should reflect back to a short wavelength, which this is short compared to what some other wavelengths could be. Okay, last part we're going to do is now take that frequency and solve for the energy associated with that fast moving particle. What's the energy equation? Anybody? E is equal to H times frequency. Plug it in. We're ready to go. E is already set up as the solution, as what we're solving for. So if E is what we're solving for, I'm going to plug in the Planck's constant and the frequency that I just calculated. What's Planck's constant one more time? Times 10 to the negative 34th units, joules per second. So that's H. What's the frequency we just got? 6.91 times 10 to the 14th per second. I'm actually going to write that as like a denominator so you understand that these 2 seconds are counter to each other, so they will cancel. So what should be the only unit remaining? Joules, which is an energy unit. So we're doing good if our units are working out. Calculate. Teeny tiny number. I'm ready when you are. 4.58. Okay, you're good. I use my whole number. Times 10 to the negative 19th. You have to put the times 10 to the blank, whatever it is, okay? That way you're showing the entire like scale of this number. It's teeny tiny. So, but this is actually for one photon. The photon is the particle of light that we're seeing. So one photon had a wavelength of 434 nanometers. It has the frequency of, super duper fast per second, and it has that amount of energy. Do you think it takes one photon for you to see all of this light? Tons and millions, trillions, quadrillions, okay, of photons. And so cumulatively, they can create a lot of energy because you just add up all their energy. So if I had 1,000 photons, it'd be that times 1,000 and so forth. So there are a lot of photons that make this happen. It would be very difficult to see light from just one teeny tiny photon. Yeah. It's kind of hard to quantify. You'd have to do it with luminescence. So in AP Chem we had a sediment battery made of mud battery, and so it's a battery that they put out in the ocean to run the climate data collectors that are just sitting out there in the Atlantic and Pacific Ocean. Nobody's got time to go replace those batteries if they run out, right? They're out there in no man's land. So they have these batteries they run from the sediment beneath the ocean. It's bacteria that kind of transfer the electrons, and they move electrons up and down, and they create a current. So there's this app called Mudwatts that I found, and you can buy it on. It's a free app, and it's based on this little kit you can buy off Amazon. It's a mud battery. I'm really super excited. They're out of stock right now, but I'm gonna get one. And so the mud battery has like this little LED on top, and it's the bacteria. It's called Geobacter, and then like Clostridium difficile. Anyway, so the bacteria make the electrons kind of move. It makes the light up. You take a picture of it with your phone, and then it tracks your electricity production over the course of the week. And it's like a challenge across the United States. So I'm about to get this and win against all these like 9-year-olds that get this. And anyway, so it just takes the luminescence of the battery or the LED to quantify the electron volts, which is the energy. I'm really excited. Sorry, let me calm down now. Okay, because I told my kids I'd buy it, but I haven't had a chance yet. Okay, let's stop here for a minute. Let's talk about spectra, and then we're moving back to lab. Because I think this will give you a chance to work within your groups. This is all the stuff you guys did Friday. At the end, we'll do some problems at 5 together. Okay, so you guys saw this on your video, right? Sorry. So in our lab, we're going to use spectroscopes. Spectroscopes, have you guys ever seen the prism on the Pink Floyd shirts? Has the prism, white light goes in, rainbow light comes out? Okay, well, it's because there's a prism, there's a diffraction grating on the inside of a prism, just like we have in our spectroscopes, which we're going to see in a second. And whenever we put light through that prism, it separates it into those wavelengths. And as you separate into wavelengths, we see the individual colors that those take on, which is what you saw on your POGL worksheet. So whenever we get out in the sun, we might see a continuous spectrum because that's just how the sun works. Different elements have a fingerprint called their atomic spectra fingerprint, which gives them very specific energies that they give off. Well, those specific energies are simply because electrons fall in different orbits. So we might see an emission spectrum called the bright line spectrum for hydrogen, which looks different for beryllium, which looks different for lithium, and everything. So every single element has its own little DNA kind of fingerprint of its emission spectrum. So you're going to see this one's for hydrogen. And on the spectroscopes, it's really difficult to see, so I have to cut the lights down, but there's little numbers underneath. There's little numbers like 7, 6, 5, 4, 3, 2, and so forth underneath the lines that kind of start to come up. Those are going to give you information about the wavelength that we'll just have to convert to the appropriate units, because they write 7, which they actually mean like 700 nanometers. So that's what's here. I'm going to come back to some of this stuff you guys saw in your video. Just hold your horses. Okay, so write down this information, and I would probably write it down on a lab sheet because we're going to go back to the lab unless you want to take it later. So the word radiation doesn't mean anything other than energy. So radiation means energy, and so the energy we are implementing a variety of wavelengths. So we're going to assign a wavelength to it in the term called angstrom. A with a halo. Do you guys remember seeing that a while ago? So I can start giving you some of these units, and actually we're going to learn what these units mean, what do they refer to. But we've actually seen them maybe once or twice before in through-dimensional analysis. So a single angstrom is equal to 1 times 10 to the negative 10th meters. That's one way of writing the equivalency. That's like me saying 1 meter is equal to 1,000 millimeters. So it's just a conversion. Or you can say 1 meter is equal to 1 times 10 to the 10th angstroms. What's different about these two? The power, because I've switched the labels. Either use 1 meter equals 10 to the 10th angstroms, or 1 angstrom is equal to 10 to the negative 10th meters. They're flip-flopped. So don't mix those up. Just use one or the other, and it'll be written out in your lab as well. So that's the SI unit for wavelength. We're going to start getting into the lab here in a second. But as you can see, the fingerprint of the bright line spectra are different for a lot of different gases. And it does have to be a gas because I will send electricity through it to excite the electrons. They get excited. They can't sustain that excitement for long. What do you call the state when they're excited? Excited state. And then when they come back down to calm, ground state. And so that difference in energy between excited state and ground state gives us this beautiful light. Okay. Let me have you guys come back to the lab with me, and then we'll kind of get started together, and I'll leave you alone. Come on back. Get in yourselves 2 or 3. You need to have access to lab. Okay, so get groups of 2 or 3. Grab the lab notebook. Grab the lab notebook. And then take the getting your 2 or 3. Have one of your partners and grab a spectroscope. Have one of your partners come and grab a spectroscope. Space right there as well. Alright, let me give you 2 instructions before I actually explain this thoroughly. Ready? Stop for 51. Listen, close the lab notebook. We'll build a lab called Spectroscope Lab 2, which I modified it. Read the beginning. Come and grab a spectroscope if you've not grabbed one. I think I have like 10 in the back. Sorry, you smell. Multiple choice response first. Multiple choice response first. Multiple choice or free response first? Spectroscope lab 2. Hold on, I'm getting modified. So I'm going to give you a heads up here for how to set up. So you do not have to go in order here by any means, but I want everybody to go ahead and grab a spectroscope. I saw lots of extras, and I want you to look up at the light above us. When you grab a spectroscope now in your hand, okay, one more time. If you don't have a spectroscope, come and grab a spectroscope. There are extras back there. As many as you can. There are lots of extras. Please come grab a spectroscope. There are 2 more. Okay, I'm going to move on because you can't follow instructions. I'm going to keep moving. So many of us have a spectroscope in our hand. The little Carolina biological symbols probably on the top. On the right hand side, I have a little slit. On the left hand side, I have this actually have the diffraction gradient. So in that orientation, that's how you're looking up. So when you look at the light above you, you look through it, you guys should see a rainbow of colors above the 7654. Yes? Say yes for me if you see it. Yes. Say no if you don't see it. Okay, so most of us, you have to get a direct source of light into the slit. You're going to see on the left-hand side the rainbow colors. Approximately what line do you see the green at? 5 point. I'm saying like maybe around 5.5, give or take. So 5.5, give or take. I have this, mine's a little wonky, my diffraction gradient is slightly thin, but yours is probably better. Okay, so I grabbed the first one. But at this point, if you look at the very top of the reading, listen. Look at the reading. Look at actually the reading in front of you in the book. You see that it says at the very top, the line on the numbers on the spectrum strip representing 1,000 angstroms. Do you see that? You need to take that number. We saw 5.5. What is that in angstroms? 5,500 angstroms. Then you can convert that to meters. And you can do some math. Okay? Start wherever you want, but I'm going to put the lights down. Everybody has a different colored lamp. So when it says frosted bulb or colored bulb, we have green, yellow. I think they have a black light. They have red. These are the 2 white lights. So you guys can plug these in. If you need to go look at the sun, I'm not sure how sunny it is yet, so maybe towards the end, and you guys can look through the spectroscope for the sun, not yourself. But please start wherever you need to on there. I'm expecting you to get about half done today. We'll have another day for this as well. All right, lights on, so I can put the lights off. So a couple of notes. So I'm going to do some oral instruction. Forgive me, I will write this in the order if I need to. The mercury source, you see the question that says Hg. Hg. Hg is mercury. That is the light source right here called the Jesus light, as we call it. This is the Hg mercury light above us. Frosted bulbs are round. Fluorescent are these white ones. I have some fluorescent, I have some incandescent, but look for me here. The only thing I will say is I will call groups over to me to look at the different hydrogen, mercury, or hydrogen, neon, helium sources. I have a special device I have to set this up on. So look, do a field for it first, then you come to me. Share the spectroscope. Here's a white light from this side of the room.
What was it?